Hey everyone, we're going to go ahead into the third section of this unit. And my hope is that you're noticing that the information is actually going kind of quick because we're not going as detailed as has been necessary sometimes in the past. Not necessarily focusing so much on the equations, but making sure you understand at least how these things are going to work out. Now, in the last video, we were talking a little bit about how they are arranged, and we talked about the orbitals and the distance that we travel, the likelihood that we'll find a given electron. Now we're actually going to go through and find out what's called the electron configuration. Some of you may have been reading in the study books, and I know that it tends to be a little confusing on there, but the goal is that by the end of this, we want to be able to write the electron configuration for a given element. And one of the ways that we're going to use this is I'm going to use our periodic table, show you using the periodic table how to be able to write the electron configuration. Now, we want to be able to demonstrate this by the end of this video. So, excuse me, work with me as we walk through, and hopefully we can answer all your questions. Now, there are three main principles that we're going to use to understand what's happening with electron configuration, or with the atoms in general, or electrons in the atoms. The first is going to be the off-ball diagram. Now, as protons are added one by one to the nucleus, we also have these electrons that are being added to the outer orbitals, just like we talked about with hydrogen. Each of these, of course, being blocked out are s orbitals, p, d, and f. Now, an oxygen atom has an arrangement, an electron arrangement of 2 electrons in the 1s subshell, 2 electrons in the 2s subshell, and 4 electrons in the 2p subshell. Where did these come from? How do we know what these shapes are? Remember, we talked a little bit about it in class. We have our different blocks, and basically those correspond to some these subshells that we actually have these electrons sitting in. Each one can only hold a certain amount, and we talked about that a little bit as well. In each part of the orbital, we can only hold 2 electrons, and within the entire sublevel, we can actually hold a certain amount given based on the number of those subshells that are there and available. So, the second rule that we look at is called Hund's Rule, which basically says the lowest energy configuration for atoms is having the maximum number of unpaired electrons allowed by the Pauli exclusion principle. In other words, if I'm looking at here, and this is my 1s, this is my 2s, and 2p. If I've already filled my 1s orbital, already filled my 2s orbital, these each represent electrons, of course. If I have, say, nitrogen, instead of going like this, which is what we'd expect to happen, the electrons will actually fill in such a way that it will give each of them the lowest amount of energy needed to expend. So instead, one will go into each space. I equated in my mind to riding the bus. If you know that there are enough seats so that you can have a seat by yourself, most people tend to try to do that. The same thing is going to happen with our electrons. When they do this, we call them degenerate orbitals, or they have the same amount of energy in that orbital. Okay? Now, this is an idea of what we call an orbital diagram. Given the amount of spaces in the orbital, it allows us to see how many electrons are in or applied in each of these. If we're looking at what we had for oxygen, this is our shorthand, our usual shorthand notation, 1s2, 2s2, 2p4. It's telling us in our 1s orbital, there are 2 electrons, 2s orbital, 2 electrons. In our 2p orbital, there are 4. Now, note that once we filled each of these, then we're able to come back and to add this extra electron here. Okay, so when we have those degenerate orbitals, usually how it'll work is each one gets one, it's an electron, and then we double back to fill in the spaces and double it up according to what we have to go through. Now, these valence electrons, the ones that we've been talking about this whole year, correspond to usually the ones that are going to be in our s and p orbitals. Notice that it always adds up to 8. If we were to get rid of the transition metals and the intertransition metals, we'll notice that we just have the S and P block, and that always equals out to 8. This is why we usually say our valence electrons, you can usually have only up to 8. Okay? Now, the elements in the same group of the periodic table have the same electron configuration, same valence electron configuration. So that means if I have, say, neon is going to end, well, let's see, 1s2, 2s2, 2p6. If I were to go down one, and I want to make sure that I'm saying this correct, from neon we move to argon. Sorry. If I were to look now at argon, argon is going to end 1s2, 2s2, 2p6, 3s2, 3p6. Notice we end s2, then p6. Same thing happens here. The only difference is now we changed our energy levels. So it's going to have the same valence configuration. Okay, that's why we end up with 8 in both of those with both of those elements. Now, remember I told you before we leave, before we finish this, I would show you how to go about doing this based on just our periodic table. Well, note we always start here. According to our diagram, we always start at the lowest point first. Think electrons are lazy. Now, in that first row, we only have an s orbital, so we have 1s2. If my goal is to get to this point, this is going to be, I'll do this because this is aluminum. I know that. If I wanted to write the electron configuration, basically what I'm going to end up doing is I'm going to start from this point, and I have to work my way through each of the lines until I reach the element of my choice. Okay? Now, each time I change energy levels, I'm going to show it in my writing, and each time I change orbitals, even within the same energy level, I'm going to have to show it in my writing. What do I mean? If I'm starting from here, which is my hydrogen, I'm going to say 1s, and I have to go through all the way through this first line, which is my 1s orbital, so 1s2. Then I'm going to change energy levels, so 2, starting back in the s orbital, s2, because I have to go through both. It's like drawing a continuous line. I'm now going from here into my p orbital, still in the second level though, so 2p, and I have to go all the way through 6, change energy levels, s orbital, 2, because I have to go through both, and all the way to here, 3p1. Now, what I've done effectively is map out where each of these electrons are most likely to be found, giving you sort of an idea of the neighborhood of where the electrons hang out. Now, as you continue to go down, we'll add a little bit more and more to this. And I want you guys to realize it's not anything too crazy, okay? But I want you to take your time and look through these examples, and I believe that it should start to work itself out. Now, if we wanted to look at the example that we have here, determine the expected electron configuration for each of the following. Sulfur. Well, we know that sulfur has an atomic number of 16. So that means that in my electron configuration, I have to have 16 electrons that are taken care of. Well, I'm going to follow through just like I did before. 1s2, 2s2, 2p is where I actually should be. 2p6, 3s2, 3p4. This would be my electron configuration for silicon. Now, I can continue to go through this, and the further I go down, the more I'm actually going to have to add, because that means that I also have to go through more and more levels. If I can go back, I want to show you something really quick, and this is something that a lot of people will miss. If I'm looking here, notice that I started off my 4th energy level, my 4th period, and I have a 3d orbital. That's something I want you to think about, because when we come into class, we should be able to start to understand a little bit of why that is. Same thing is going to happen here. It shows us that our f orbital actually goes in right here. And we notice that when we jump into our f orbital, we start off at 4f, even though it's on the 6th energy level. I wonder what's going on there. And that's what I want you to start thinking about. How are we going to figure out what's going on, and why is it that in each of these, for the d orbitals, we drop 1 level, and for the f orbitals, we drop 2? Well, that's actually where we're going to end it for today. Write down your questions, write any comments, response. I will get back to you as quickly as I can. Have a great evening, and see you in class.